We're here for another meeting of New England Dynamics and Number Theory seminar, and Keivan Mallahi-Karai joins us from Germany this time, far from New England, far from Old England too. And the title is Spectral Independence of Compact Groups. Welcome.
Okay, thank you very much. So thanks a lot, Dimitri. So first, I would like to thank all the organizers for having the opportunity to give this talk here. So what I'm going to talk about is based on a joint work with Alireza S, Golsefidy and Amir Mohammadi. And the paper which I'm going to present is already on arXiv. Today I would basically try to talk a little bit about sort of the background to this work and also spend a little bit of time discussing some of the ideas that go into the proof. So I think since the topic is a little bit, I think, different from the typical, or at least most of the talks I have seen in this seminar, so maybe I would spend a little bit of time talking about the background and question that we are interested in. Oops, sorry, there is some problem. Share again. Okay. All right. So there was some problem with moving the slides. Okay. So I'm going to start by talking about random walks on compact groups. You see my slides now, right?
No.
No?
Yeah, it's all gone.
They disappeared.
Coming in.
Yeah.
Now you see?
Now they're back.
Yeah, now we
yeah,
see.
Yeah.
Okay,
Yeah.
good. Right, so I'm gonna start by talking about random walks on compact groups and sort of the questions that arise when you study these type of Markov processes.
We don't.
So
I don't.
there is a problem?
I think Dimitri's internet.
This was delayed sound.
But do you see the screen or not?
Yeah.
Yeah, don't worry.
Connection is fine.
Okay, so maybe we wait for Dimitri. Or maybe I can start. I don't know what's...
You can go ahead.
I think you should start. Yeah, because I think he was freezing up. So
okay. So I just introduced some basic notation. So the questions that we're interested in are going to involve typically either one fixed compact group, which are denoted by G, or a sequence of infinitely many finite groups. And an example that you can keep in mind, in fact, for most of the talk is, let's say, you take the group G to be the group SUN of the unitary transformations of Rn, or you can take if you are interested in thinking about an infinite family of groups, you can, let's say, take SL2FP, where P is running over all the primes. So what is a random walk? So in order to define a random walk on a group, you need to have a symmetric probability measure on this. So the random walks we're interested in are basically governed by a symmetric probability measure with a finite support on the group G. And a typical example, again, that you can think of is that you pick a finite set of elements in G, which is symmetric, and then you give equal mass to all the elements of this finite set. So this is just a uniform probability measure on the finite set S. This is a very good example to keep in mind. And then once you have this probability measure, you can pick a sequence of independent random variables on this group G, which have the same distribution as mu. And then in order to define the random walk, we define the random sequence or the sequence of random variables xn, which is simply defined by xn is the product of xc1 up to xcn. So some of the idea is that you start from the identity element of the group, and then you apply a random step, which is going to take you to xc1, and then another step from xc1, which is going to take you to xc1 times xc2, and so forth. So this sequence of random variables, typically we're interested in understanding their behavior. One thing which is maybe worth mentioning here is that you can also write down exactly the probability measure, so the distribution or the law of these random variables in terms of the convolution powers of the original probability measure. So it's a standard definition that if you have two probability measures, mu and nu, you can define the convolution of these two measures by the following sum, which is essentially saying that you're taking a random quantity with distribution mu and then a random quantity with distribution nu. And then you're asking, well, if you multiply them, when do you get G? And this is on the right-hand side of this expression is precisely the probability of getting G. So now there is a general statement in the theory of Markov chains that you can apply, which tells you the following fact, that if your measure satisfies some sort of standard conditions, these are conditions that should definitely be satisfied for what I'm going to say to have a chance to be true. Namely, the measure is aperiodic, and also that the subgroup which is generated by the set F, the support of the measure, is dense in the group G. Then if you look at the probability measure mu n, then this probability measure is going to converge to the uniform Haar measure of the group G.
And what's aperiodic? Can you tell?
So aperiodic means that the measure is not on a coset. It's not supported on a coset of a normal subgroup. So if it's the case, then basically what happens is that every time you run the random walk, you're just going over cosets. So every time you're in one coset of this normal subgroup, so you can never converge to the uniform distribution. You're always stuck in one coset. The coset itself is moving, but you're always stuck in some coset of that normal subgroup. Like for instance, would be let's say if you do random walk on, let's say Z2, and every time you take step 1. So you're always 0 or 1, so it can never be both at any given time. So, but if these two conditions are satisfied, so there is a theorem, I think it's usually attributed to Stromberg, that this sequence of probability measures converge in distribution to the Haar measure of the group G, which means that if you take any continuous test function on the group G, and if you integrate this test function again against the sequence of convolution powers of this measure mu, then it converges to the integral of f over the entire group G with respect to the Haar measure. So roughly speaking, it means that if you take n steps of the walk and if you average the value of f after these n steps, this converges to the integral of G. So the sequence essentially equidistributes that group. So one question which is sort of interesting, I'm not going to really come back to this too often in the talk, so at the end I'll mention a couple of results where I think it's useful to keep this in mind, is that if you want to think about how much it takes really for this sequence to distribute in the group G, it's worth keeping in mind that, for instance, if you have a group G, let's say, think of a finite group G, and if your initial set has k elements in it, then the support of the convolution power, so maybe this k was not a good choice. So if, let's say, your finite set has n elements, then support of the convolution power would have n to the k elements. Which means that if the number of the steps that you're taking is less than the logarithm of the size of the group in the basis of the size of the set S, then there are always going to be some elements which are not hit by the random walk. So it's sort of obvious that the best chance you can have, I mean, even to hit all the elements of the group, your random walk should be run basically at least of the size log of G. That would already, I mean, not doing that already prevents some elements from being hit, which means that, well, you're still probably far away from equidistribution.
Wait, but G is, what's the assumption on G? It's,
So G is finite in this case.
G is finite.
Yeah, G is finite. But in fact, even if G is not finite, so let's say G is some group like SU2, you still have a version of this statement in the following sense that, let's say you take a random walk in k steps, and let's say, well, you're not going to hit every element, of course, but let's say you take a very small disk at some place in the group G, well, this disk, you can sort of translate it around, and you can sort of partition the group G into some translates of this disk. So again, you can make a similar type of counting argument that if you want to hit, let's say, a disk of a particular radius, then you need to at least expect to take a certain number of steps in order for this to have a chance to be true. Because let's say if you take a disk of radius r, then, well, the volume would be r to the d. So you have r to the power minus d more or less transits of this disk. And if your random walk is going to hit all of the disks of radius r, then you need to have at least the logarithm of that many steps, basically, to have a chance. This is not so important, I mean, at this point, but we come back to statements that have this sort of flavor to them. So I just wanted to mention this on the way. So, so this was sort of a dynamical way of thinking about random walks. There is a slightly different way of thinking about random walks as well, which I like to think of as a more static point of view. And that is in terms of what is called Markov operators or averaging operators. So here we take our probability measure mu on the group G and use it to define a linear map from L2 of G to L2 of G, which is just convolution with the probability measure mu. So if you want to think about, let's say, the probability measure, which is the uniform distribution on a finite set S. So in that case, you can write down exactly P mu of F. It's a very nice formula. It basically says if you want to apply this operator to a function F, and you want to evaluate it at a point G, what you have to do is to take a step starting from the point G, and then you compute F at all these points, and you average up those values. So this is just the so-called Markov operator. And since we assume that this set S is a symmetric set, so if it contains X, it contains X inverse, you can see that this operator is always a self-adjoint operator. This map sends the constant function 1 to the constant function 1. And also from the definition, it's more or less clear that the operator norm of P mu is at most equal to 1, because it's essentially, it takes a function f and it takes some translates of f and averages those translates. So the norm is at most 1. And since it takes the constant function 1 to itself, so it follows that the norm of P mu is exactly equal to 1. So this is not by itself so interesting. So what we can do is to look at the orthogonal complement of the one-dimensional space, which is consisting of constant functions, and look at what this operator P mu does on its orthogonal complement. So because it's self-adjoint, it takes this orthogonal complement to itself. So it defines a linear map. And again, the norm is going to be obviously less than or equal to 1. Sometimes instead of working with the norm, we look at the logarithm of 1 over the norm. So this is essentially a slightly different transformed version of the same quantity, which instead of taking values between 0 and 1, takes values between 0 and infinity. And here we have the notion of spectral gap, which says the following, that the probability measure mu is said to have a spectral gap if lambda of mu is less than 1, strictly less than 1. Or if you are dealing with, let's say, an infinite family of groups and some probability measures on them, then what you would like to be the case is that the lambda of these mu n's, all of them are staying away from 1. So there is an upper bound for all of them, which is strictly less than 1. So this is a notion of spectral gap that can be defined essentially for a random walk on a compact group. Okay, so there is a slightly different point of view, which is useful as well. I mean, when you think of random walks. So this is in terms of the so-called irreducible unitary representations of the group G. So if G is a group, compact group, you can look at so-called unitary representations of G, which are just group homomorphisms from G to the group of unitary maps of some Hilbert space. In the case of compact groups, I mean, it's a standard theory, I guess going back to Hermann Weyl, that that all of the irreducible representations of compact groups G are always finite dimensional. And if you take an arbitrary unitary representation, so for instance, L2 of G, this representation decomposes into a direct sum of irreducible representation. So the theory in some sense is very similar to the theory of finite groups, with the exception that there are infinitely many representations, irreducible representations. And now, if you have a probability measure on the group G as well, you can also define pi of mu for any irreducible representation, for any representation of the group G, in the following way that, well, you take pi of, so you take this probability measure mu, and you can use it to average up the operators pi of G for G in the group G. So effectively, what you're doing is that, let's say if your probability measure is just the uniform measure on a finite set, pi of mu would be just the averages of pi of G for G over the same finite set. So the good thing about this is that, so this operator essentially is going to be the, you can view it as a restriction of the initial operator P mu. So if you take, let's say, P mu as a map from L2 of G to L2 of G, and if you sort of break down L2 of G into these irreducible components, so this pi of mu essentially tells you how this P mu acts on these irreducible components of the group. And if you want to look at the question of existence of spectral gap for the probability measure mu, what you effectively have to do is to look at each one of these operators, which is basically a map on a finite dimensional space. And then you look at the spectrum, and then you would like to see whether the supremum of the spectrum of each one of them, of all of these operators, does it approach 1 or not? So just to give maybe a idea of what is, how, right, is one way of thinking about these things. Like in the case of the group R mod Z, which is the circle, the irreducible representations are just the maps defined by 2 pi I n x, and this pi of mu is just the Fourier transform of the measure.
Sorry, so n is missing in the exponent.
N is missing, yes, yes. Sorry, yes.
So pi is pi n.
That's correct. Yeah. So it's pi nx. Right. So there is there is an n missing here as well.
Okay.
Right. So now one thing you can actually do with a spectral gap is sort of its application to constructing a certain type of graphs, which are called expanded graphs. So I'll quickly mention what expanded graphs are. I think everybody probably knows the definition. Just quickly go over the definition. So let's assume that we have a family of finite connected k-regular graphs. So we call this family an expander family if you can find some epsilon, so that if you look at the eigenvalues of the adjacency matrix of these graphs, then aside from the eigenvalue, the top eigenvalue, which is equal to k always, the rest of the eigenvalues are away from k. So there exists some epsilon so that all of the eigenvalues are less than k minus epsilon. Of course, for this to be interesting, we need this family to be an infinite family of graphs. So of course, for any finite family, there would be, if they're connected, then all of the eigenvalues are away from, are not equal to k. So there would be an upper bound. But for an infinite family, even the existence of such a family of graphs is not clear. So this notion is also, you can also express it in a combinatorial language. So you can see that essentially having a gap between k and the next eigenvalue is equivalent to the following combinatorial condition, that if you pick a subset of the set of vertices, which is is not very large, so in its size is less than half of the size of the vertices, then this set is going to have a large boundary. So the size of the boundary of this set is comparable to the size of S itself. So the sets kind of grow if you pick a set which has a room to grow, it will grow always. So the first construction of expanded graphs was done by Margulis in 1973, and this construction was based on some representation theoretic property of lattices, which is called convergence property T. And this basically raised a lot of interest in sort of applying group theoretic techniques to constructing graphs of this type. And maybe the next breakthrough in this direction was the construction of optimal expanders, which are called Ramanujan graphs, which was done basically independently by Lobatsky, Phillips, and Sarnak, and Margulis in 1988. So these are graphs that, in some sense, are optimal expanders. Doesn't matter for the sake of this talk what they are, just part of the history I mentioned. And then maybe the next breakthrough, which is really important for the sake of today's talk, is the work which was done by Bourgain and Gambert in 2006. And what they did was that they basically approached this question of constructing expanded graphs from a completely different point of view. So this does not really have any representation theory in it. There is a tiny input from the representation theory of finite groups, but otherwise, it doesn't deal with anything like convergence property T or other sort of tools from representation theory that, let's say, came up in the construction of Ramanujan graphs. And this construction deals with the following setting. So you pick a subgroup of SL2Z, which is Zariski dense. So you basically pick two elements that do not commute, and they're going to generate a Zariski dense subgroup. And then look at the projection map from SL2Z to SL2Z mod PZ. So you reduce all of the elements in this group modulo P. And you can see that, except for finitely many primes, this map is going to be surjective. And what Bourgain and Gambert proved was that if you look at the Cayley graphs of SL2Z with respect to the projected generating set, this family of graphs that you obtain would be a family of expanders. So here you can pick gamma to be a very completely arbitrary group, so that you have a lot of room basically to choose gamma. And this construction essentially solved a lot of open problems in this direction. So before this construction, it was not, for instance, known that if you take, let's say, the group which is generated by the unipotent matrix 1, 2, 0, 1, 3, 0, 1, and its transpose, whether this group satisfies this property. This is a so-called Lobatsky's 1, 2, 3 problem. So even for specific groups like this was not known. And Bourgain and Gambert, using a completely different strategy that I will say a couple of words about later, actually solve this problem. So, okay, so I want to now sort of shift gears and start sort of talking about a couple of other concepts which are related to the talk today, and this is the notion of coupling of measures. So the notion of coupling is a very general notion, it's a very fundamental notion in probability theory. So if you have two measure spaces x1 and x2 and two probability measures mu1 and mu2 on the spaces, a measure which is defined as the Cartesian product of these two x1 and x2, this is called the coupling of mu1 and mu2, if the marginals of this measure mu are precisely mu1 and mu2. So this picture sort of explains what you expect from a coupling. So what we want from a coupling is that we want to have a measure or the Cartesian product with the property that if I pick any subset, here I have a subset A in x1, and then I look at the pre-image of this subset in the Cartesian product, which is A times x2, I want mu of this pre-image to be exactly equal to mu1 of A. So the marginal probability measure of mu to be exactly equal to mu1, and similarly, the marginal on x2 must be equal to mu2. So this set of couplings is always easily seen to be a closed convex set in the set of all measures on the Cartesian product. And in the special case that these measures are finite, that x1 and x2 are two finite sets. So you look at really linear algebraic setting in which these are the finite sets and you're looking at two measures on them. These couplings are just described by, let's say, matrices where the rows and columns are supposed to add up to specific numbers. And this is defining something which is called the transportation polytope in some Euclidean space. And people have studied this transportation polytope from other fields, even from applied areas. there are lots of interesting questions like, can you characterize the set of vertices of this polytope somehow combinatorially in terms of mu1 and mu2 and so forth.
Keivan, is coupling the same as joining in different?
I think joining. I think it's usually applied. I think for when you have a group action. I mean, at least this is the way I have seen. But I mean, you can use the same. I think this term is used in probability theory. This notion of coupling, but we chose this term. I mean, but I mean, joining I've seen also used for, let's say, if you have two actions, let's say on G actions on x1 and x2, and you want to have an action that projects into.
Okay, but I thought that joining is a measure also, but okay.
Okay, I mean, all right. So I mean, I think yeah, we call it coupling.
Different language are the same.
Yeah. Okay.
Okay.
All right. So right. Okay. So now let's assume that we have two compact groups. So this was basically x1 and x2, which is measure spaces. Now we're back to the setting of compact groups. So we take two compact groups G1 and G2, and we take two probability measures on G1 and G2. And let's assume that both of these measures are known to have a spectral gap. And now let's take some measure mu, which is defined on G1 and G2, and its marginals are mu1 and mu2. So it's basically a coupling of mu1 and mu2. And now you can ask, does it follow that this measure mu also have a spectral gap? So roughly speaking, what you see is that if you do the random walk in G1, according to the measure mu1, you are going to equidistribute exponentially fast. And the same goes for mu2. Now the question is, if you do a random walk on the group G, again, do you converge to the uniform distribution, to the Haar measure exponentially fast? Well, if you think about it for a second, you realize that this is not true. And here is maybe the easiest counterexample. So you take, let's say, G1, G2 be the same group. And let's take these probability measures to be maybe the Haar measure. So any measure that has spectral gap. So the Haar measure is maybe the optimal one. And then, so take the probability measure mu to be the measure which is sitting on the diagonal. So essentially you take the diagonal, which is just a set of pairs G and G, and you push forward the measure mu to this set. And this is just a Haar measure on this group. So it's just a Haar measure of G on this subgroup. So this measure, you can easily see that if you project it onto each one of these factors, so the measure mu on this diagonal group projects to the Haar measure as well. So you have spectral gap for both of the projections. However, the measure itself certainly does not have spectral gap. In fact, if you do the random walk according to this measure, you will never leave this subgroup G diagonal, which means that, so it's sort of like, obviously it does not have a spectral gap. You can essentially do a similar construction. So let's say if you have two groups G1 and G2, which have a non-trivial common quotient H, you can basically look at something that looks like it's diagonal. So you look at the pairs G1 and G2 in the Cartesian product, where so phi1 is the map from G1 to H, the homomorphism from G1 to H, and phi2 is the homomorphism from G2 to H. So if you look at this sort of diagonal looking subgroup of G1 times G2, again, you can see that you can sort of push a measure. So if you look at the push forward of, or not push forward really, but you can construct a measure on this K, which again projects down to the Haar measures of G1 and G2. And again, because this measure is defined on a subgroup, it has no chance of having a spectral. So in general, the answer to this question is no, but of course, these examples, I mean, you see that something is sort of wrong with these examples. And what we're interested in is, well, what can be done? I mean, is there some positive statement that can also be said here? So let's set some definition. So we take, let's say, two compact groups, G1 and G2. And then we say that these two compact groups are spectrally independent if the following holds, that if you take any two measures, mu1 and mu2, on the groups G1 and G2, and if you know that both of these measures have a spectral gap, so this L, if you remember, was the minus log of 1 divided by lambda 1. So this being positive is just equivalent to saying lambda 1 is less than 1 and lambda 2 is less than 1. Then what we want to be the case is that if you come up with any coupling of these two measures, then that coupling also has a spectral gap, and we want the spectral gap to be bounded from below by a function of C naught. So let's say if you know that if you know C naught, you want all of the couplings of mu1 and mu2 not only to have spectral gap, but in fact a uniform spectral gap. All right, and what we have, this basic observation that we just made in the previous slide, basically says that if there are any spectral independent groups, then they have to be algebraically independent in the sense that they do not have, they should not have any common non-trivial quotient. And the good question you can ask is the converse true? So if there is no obvious way of constructing a measure on the Cartesian product of two groups that, let's say, like in the previous examples, does that say that the groups are spectrally independent? So the answer is that it's a little bit complicated. So the first theorem, which I want to mention, is a positive answer to this question in some setting. So let me just go through this and explain the result. So in this setting, we pick GI, so the blackboard GI, to be an Fi simple, almost simple algebraic group over Fi. So Fi is either could be the field of real numbers or it could be a p-adic field. So you pick some algebraically, you pick an almost simple algebraic group over RQ or QP, and then you look at the set of Fi points of this algebraic group. And then you take little g, so GI, the standard GI, to be an open compact subgroup. So I think a typical simple example you can think of would be, for instance, you take SU2 and SU3. This would be, for instance, examples. Or you can take SL2 of ZP. If SL2 of QP, let's say, would be a GI, and then you take some compact open sets there, which would be, for instance, SL2 of ZP. And now suppose that these groups G1 and G2 are not locally isomorphic, which in this case means that their Lie algebras are not isomorphic. And now suppose you have a probability measure on G1 and on the Cartesian product of G1 and G2. And you know that the marginals of this probability measure, so I think I didn't say mu is a coupling of mu1 and mu2. And the marginals, mu1 and mu2, they both have a spectral gap, which is bounded from below by C. Then the claim is that the measure mu itself has a spectral gap, and the spectral gap is bounded from below by a function which depends only on C and, of course, the groups G1 and G2. So in particular, the groups G1 and G2 are going to be spectrally independent. So basically, a special case of this theorem would say that like SU2 and SU3, because they have different non-isomorphic Lie algebras, they would be spectrally independent. Or these groups and SL2 ZP, for instance, would be spectrally independent. So one thing which is interesting to mention here is that, well, of course, this theorem, I stated it for simple groups. It turns out that the statement is false for abelian groups. So there are abelian groups. So this is the example that we worked out in the paper. So if you take R mod Z, so the circle group, and if you take p-adic integers, these two groups, even though they're algebraically independent, so algebraically they have absolutely nothing to do with each other. There is no map from one to the other one. So there is no sort of diagonal construction similar to the one which I showed you before. But nevertheless, they are not spectrally independent. So you can construct a coupling of the Haar measures on R mod Z and ZP, which does not have a spectral gap. So this shows that basically, in some sense, the question is somewhat more subtle, and it has to do with algebraic properties of the groups as well. So maybe I say a couple of words about the connection between our theorem. So the next theorem, which I will mention, also has some connection to the expander graphs. So after the work of Bourgain and Gambert, the method that was used by them was in fact used by many other people to prove similar statements in other settings. So one sort of a statement conjecture which I want to mention here is that is the following. So let's say you pick a finite symmetric set inside GLN of Z, possibly of 1 over Q naught for some integer Q naught. And you assume that if you look at the group generated by, sorry, this is omega, it's a typo. So if you look at the group generated by omega, this group has a Zariski closure, which is a perfect group. So it means that it doesn't have any non-trivial obedient quotient. And then the conjecture is that, well, if you pick, in this case, this group gamma, and if you reduce it modulo m, so m runs over the set of positive integers, then you get a family of expander graphs. Over the integers, I'm sorry, integers that are coprime to Q naught so that this reduction map is defined, basically. So this conjecture has been established, or at least is supported by several results. I mean, that came after the paper of Bourgain and Gambert. So I just quickly mentioned, so the Bourgain, Gambert, and Zarnak, they proved similar results in the context of affine sieve. So the result was extended from SL2 ZP to SLD Z mod QZ by Bourgain and Varyu in 2012. And then Varyu also proved a similar statement for SLD over sort of more general rings. So these are the ones that are obtained by a ring of integers of some extension of Q. In the work of Golsefidy and Varyu, they proved essentially this conjecture, a special case of this conjecture. So again, for perfect groups, but the mod, so they can only apply it to M where M is square free, so it's a special case. And then there are other cases in which you can prove similar results, again, sort of more restricted results. So in 2 other works of Alireza, so where, in the first work, you have to restrict to the case of semi-simple groups. And in the second one, you work with the setting in which M runs over the set of prime powers. So some cases, some special cases of this conjecture are proven. The last one, which I want to mention as well, deals actually with the case that you have omega inside SL and Z, and the Zariski closure of gamma is Q simple, so you have some condition, some rather strong condition on gamma, but here M is allowed to go over all of the integers. So that's in some sense one case in which you're allowed basically to let M run over the set of all integers. And in these cases, each one of these theorems basically give you a family of expanders. So the second result that we proved with Alireza and Amir is the following. So as before, we take G to be an absolutely almost simple Q algebraic group, and we pick the finite symmetric set inside the group of rational points of G. And we assume that the group which they generate is Zariski dense in G. So now we pick a set of finite places of Q. So these are basically set of prime correspond to a set of prime numbers, or you can take also Archimedean places, with the condition that the points of G over the completion of Q with respect to these places is a bounded set. So for instance, let's say if you take these matrices with integer coefficients, then you can take all of the prime powers, every prime. So you can take basically V, go over any finite place, and then you land inside G of ZP. So now for 2 distinct places, nu1 and nu2, you take gamma nu1, nu2 to be the closure of this group gamma inside the Cartesian product of these 2 groups. And then the claim is that if you run over all of the pairs of nu1 and nu2, which are distinct places, then inside V gamma, then all of the, so if you look at the probability measure mu projected down on this group, they all have a uniform spectral gap from below. So this theorem also essentially gives you a family of expanders, but this, in this setting, the groups over which you're actually working would be sort of Cartesian products of 2 groups of this sort. Okay, and then maybe I say a few words about about one of the ingredients of this proof, which is also one of the results that we prove in the paper. And this is a notion of, it's an interesting notion in its own right. It's a notion of stability and local stability. So the notion of stability actually is a very interesting notion, sort of in its own right. And it sort of comes from the following setting. So I'm going to define vaguely at the moment the notion of an approximate homomorphism, and I try to make it precise in the statement. So an approximate homomorphism between two metric groups G and H is simply a map from the group G to H, which satisfies the condition of being a homomorphism up to an error of size epsilon. So it means that so there is some epsilon positive, so that if you look at phi of G1, G2, and if you compare it with phi of G1 times phi of G2, these are two elements of H. What you would like to be the case is that these two elements are not necessarily equal, but they are not too far apart. They're not more than epsilon apart from each other. So, of course, in order to make this precise, you need to have a metric on the group H, and you can, in principle, put many different metrics. If you have a Lie group, you can have a metric which is, let's say, coming from the Killing form or from embedding of your Lie group inside some GLN. But also, you know, if your group is a discrete group, even in these cases, people have looked at this problem with many different metrics. So, of course, you can ask, you know, how do we get these approximate homomorphisms? Well, one way of getting sort of very cheaply an approximate homomorphism is to start with an honest homomorphism from G to H, and then just add some error to this. So if you have a perturbation of a homomorphism, this is going to give you an approximate homomorphism. So this is, of course, one way of constructing such things. And now you can ask, and this is called Ulam's stability question. I think Ulam asked it in a very specific setting, I think for maps from R to R, I think the question was, that if you have a map which is an almost approximate homomorphism, so if it satisfies this, is it always a perturbation of a homomorphism? So do you always nearby have a homomorphism so that this phi is basically a noisy version of this real homomorphism? Well, one of the first results in this direction was proven by Keivan. So he actually proved, this is a result in the context of discrete groups, that if you have an approximate homomorphism from an amenable group to the group of unitary operators on the Hilbert space. So here, H is the group of unitary maps on a Hilbert space, and the domain is some amenable group. Then the answer to this question is yes, so you can always correct an approximate homomorphism to get a homomorphism. As I said, this result has, in the last few years, there are many works actually in this direction they consider different metrics on G and H, and there are both positive results and negative results. So for compact groups, there is an old work by Grove, Karcher, and Drew, who proved essentially that approximate homomorphism between compact groups are actually near homomorphisms. The setting that we are interested in is actually not about approximate homomorphisms, but only about what is called approximate local approximate homomorphisms. So this is a setting in which your map phi is not defined on entire group G. It's only defined on a neighborhood of the identity in the group G. And basically what you know about this map is that if you take phi of G1, G2, this is close to phi of G1 times phi of G2, but only when phi of G1, G2 is defined. So it's possible that you take this G1 and G2 near identity, but the product is outside of the domain of phi, in which case you don't get anything. But as soon as the G1, G2 lands in that neighborhood, then this condition should be satisfied. And now you can ask more or less the same set of questions, you know, is it always coming from a homomorphism? So just to mention the next result, I want to introduce a couple of notation here. So if the group, we take a topological group G with a metric D, we denote the delta neighborhood of the identity by this notation I sub 1 sub delta. And I want to use this notation equality with subscript delta just to say that 2 points are at most delta apart from each other. So One more notation is the notion of a delta thickening of a set. So if you take a set B, the delta thickening of this set is just the set of points that you get basically by starting from an element of B and then moving by at most distance delta. So it's basically bit X, where B is in B and X is a point in the group at distance at most delta from the identity. This is what we call the delta thickening of the set. So this is like a picture of this. And there is this other notation, which is, we didn't use this notation in the paper, but I think it's maybe not bad for the talk. So this is inclusion at scale delta. So if I have two sets A and B, I say that A is a subset, and then there is this delta here, B, if the delta thickening of B contains A. So here, for instance, B is just this curve. And if I thicken it, then I get this blue region, and this contains a set A. Of course, A is not a subset of B. So this is the third result of the paper, which is used actually in the proof of the theorem 1 and theorem 2. And I want to go through the statement. So this theorem has two parts, one for real and one for p-adic groups. There is, in fact, a more general statement in the paper, but this is maybe easier for a talk. So let's take G1 to be the unitary group SUN1 and G2 to be the unitary group SUN2. Then the claim is that you have some number M0 bigger than 1 and some C less than 1, depending on N1 and N2, such that the following holds. So suppose you have a map from a neighborhood of identity inside G1, so the row neighborhood of the identity in G1, to the group G2, which is basically row to the M homomorphism. So f of G1, f of G2 is f of G1, G2, row to the M, and f of G inverse is f of G inverse row to the M, close to each other, basically. And I want that, we need that the image of this map, well, you can, for instance, send everything to 1 or to some very small set, for instance. But we would like to assume that the image of this map is not too small, in the sense that if you thicken it by row to the M, then it contains a slightly larger neighborhood of the identity. So it contains a neighborhood of radius row to the M divided by M naught. So let's say M over 2 or something like this. So this M0 depends on G1 and G2. So if you are in this situation, so if you have such a map, which is almost local homomorphism and has large image in this sense, then the claim is that this can only happen if N1 is equal to N2. So you're dealing essentially with one group, and the map F, which we dealt with, is essentially a perturbation of an isomorphism from SUN to SUN. So this, I have to be a little bit more careful in stating it. So it means that if you look at a ball of radius rho to the M, so this is smaller somewhat than the original ball, then f of g is a perturbation of size rho to the Cm, so C is the constant whose existence was mentioned here, of this isomorphism psi. So roughly speaking, almost homomorphism are essentially perturbations of isomorphism. So this theorem has also a p-adic analog, which maybe I just very quickly mention, because I want to also say a couple of words about the proof of the results. So in the p-adic setting, you need to, again, sort of think about the neighborhoods of identity. So, one of the good things about p-adic groups is that, in fact, neighborhoods of identity, or you have a family of neighborhoods of identity which are themselves actually subgroups of the group itself. So let's pick SL and ZP, and let's look at the following congruent subgroups. So these are the elements of SL, and there's a typo here. This is SL and ZP, which are congruent to the identity modulo P to the K. So this is a subgroup of finite index in SL and ZP. And this subgroup is precisely, with respect to the very natural metric, is just a ball of radius P to the minus K in the group SL and ZP. Okay, so this is the local stability result for p-adic groups. So as before, we take N1 and N2, and we take, and we're interested, so let me just say what we're interested in. We're interested in the maps which are defined on the following group. So this is really group homomorphism. So SLN N1 of ZP. So this congruent subgroup, which is, you can sort of view this as a neighborhood of the identity inside the group SLN ZP. And here we have, you might say, well, this is not about approximate homomorphism, but not about group homomorphism. But if you look at it, you see that this map goes into SLN2 of ZP modulo this congruent subgroup, which you can interpret as a map which goes inside SLN2 ZP, but it can basically, you're allowing an error which is of the size p to the minus km. So this having a genuine homomorphism into this group is equivalent to having a homomorphism into the group SLN-Z2 of ZP, an approximate homomorphism into the group SLN2-ZP, where the error is of the order p to the minus km. Again, we need to assume that this homomorphism has a large image, so the image contains sort of a fat congruent subgroup inside. Then the claim is that in this case also you need to have N1 and N2 to be the same, and this map that we had here essentially is coming from and this isomorphism size. So there is this isomorphism that if you restrict it to the ball where this is defined, so f of this coset is essentially congruent to psi of g modulo p to the ckm, and c again is some constant that depends on N1 and N2. So this is exactly the same statement, but for p-adic. Okay, so Dimitri, how many we finish after? How many more minutes do I have?
Well, I mean, the closing time is 1:30. You can finish earlier and then ask for questions.
Okay, maybe is it okay if I speak for 10 more minutes? Is that because I want to say a couple of words about the proof as well?
That's fine.
Okay, thanks. Okay, so maybe I say a couple of words about some of the ingredients of the proof. So one of the ingredients of the proof is a notion which was introduced in the previous paper with Alireza and Amir, and that's a notion of locally random group. So a locally random group is a compact group which has the following property, that if you pick any unitary representation of this group pi, then this unitary representation has the following sort of Lipschitz property, that if you pick any two elements of the group, the distance between pi of x and pi of y in the operator norm is bounded by a constant times the distance between x and y in the group G. And this Lipschitz constant is only dependent, so it sort of polynomially depends on the dimension of the of that representation. So I say a couple of words why these groups are interesting, but as a non-example of a family of locally random groups, just take the group R mod Z. So if you take the circle group, and if you take pi to be the one-dimensional character e to the 2 pi I and x, so you can easily, so for all these characters, the dimension is equal to 1. So effectively here you have a constant. And what you would like, I mean, if this group wanted to be a locally random group, then essentially all of these characters had to be Lipschitz uniformly, so with the same constant. But it's obvious that if you if you make n large enough, these maps would have Lipschitz constants which are getting bigger and bigger. So R mod Z would not be a locally random group. However, if you take real p-adic Lie groups or real or p-adic Lie groups with simple Lie algebras, like SUN, for instance, they would be locally random. So this is something that was proven in the previous work. And then a little bit of additional notation. So, so the notion of thickening, which I defined in the previous in one of the previous slides, you can sort of use it to also define similar notions on functions. So if you take a function from G to R, you can define the following function, which I denote by f sub eta, which is the convolution of f with the map p eta, which is the normalized characteristic function of a ball of radius eta. So you take a ball of radius eta, so it has a characteristic function. You sort of turn it into a probability measure by just dividing by the volume of the ball. And the map f eta is the convolution of f with p eta, which means that what you do is that you start from one point and you look at all of the ball of radius eta around yourself, and you average up f on this ball, and this would be the value of f eta at a point x. So effectively what you would like to do is that if f, let's say, makes some oscillations in a very small ball of size eta, when you're considering f eta, you're trying to flatten all of these oscillations. You sort of replace it by the average value of f in that ball. And similarly, you can define the same notion for measures. So if you have a measure mu, you can look at the convolution of mu with this probability measure, and that gives you another measure which is always continuous. Even if your initial measure, let's say, is only supported on a finite set, this measure is going to be having is going to be continuous with respect to the Lebesgue measure, with respect to the Haar measure. So one of the interesting things about locally random groups, one of the useful facts is that if you have a locally random group, G, so L locally random group, so L was the exponent in the, maybe just mention it here. So L is the exponent in the definition. We have the following mixing inequality. So if you take two functions in L2 of G, and if you look at the convolutions, you have the following upper bound for the L2 norm of the convolution. So to put this into some context, just if you ignore this term, so completely the first term and the exponent here, you see that the fact that this L2 norm is bounded by the product of these two L2 norms, this is just the Cauchy-Schwarz inequality. So if you have a locally random group, this inequality basically tells you that if you sort of ignore, if you can control somehow the L2 norm of these two flattened versions of the function f, so f eta and g eta, then you have the following sort of contraction. So you have the L2 norm, you can sort of bound it by this eta to the power of 1 over 2L times the product of the L2 norms. So this is one of the ingredients of the, one of the tools that we use in the proof of theorem 1. I want to say one more ingredient, which also goes into the proof, and that's something which is called the Paley-Littlewood decomposition. So, let me just say a couple of words about how this decomposition is defined. So as a motivation, or at least some special case which is easier to understand, we take the group G to be the group of SLN over ZP. So this group, as I mentioned a little bit earlier, has the following nice property that sort of this group is filtered by a family of subgroups that provide a system of neighborhoods for the identity. So if you take, let's say, NK to be the case congruent subgroup, then this would give you this sequence of normal subgroups. And one interesting thing that you can actually do with this family of normal subgroups is the following. Remember, if you have a finite group, one thing that we could do was that we noticed that we have the one-dimensional subspace of constant functions. And in order to understand spectral gap, we sort of looked at the orthogonal complement to that one-dimensional space. So in the case of SLN ZP, we have effectively, since we have this family of this nested family of normal subgroups, at any level, we have some construction like this. Basically, we can look at, for any index I, we can look at the functions which are invariant by one of these ni's and integrate to 0 if you look at them, if you integrate them over ni plus 1. So let me just explain what this is. So we take this map from L2 of G to L2 of G, which takes a function G, and first convolves it with f ni plus 1. This is exactly this. Here we had this notion. So this p eta was the ball of radius eta, and we convolve with it. So we convolve it with the normalized characteristic function of ni plus 1, which is a smaller subgroup, and we subtract off the normalized the convolution of G with f and I. So this construction essentially gives you a sequence of functions delta I. So what you would like to do is to look at essentially the oscillations that the function G can have at different scales. So this gives you the composition of G. This is more or less straightforward from the definition into these these functions delta I of G, all of them are in L2. Any two of them are orthogonal to each other, and the L2 norm of G is just the sum of the squares of the square of the L2 norm is just the sum of the squares of the L2 norms of delta I. So you can kind of control the behavior of the function G by looking at these delta I's, which each one of them sort of records one sort of oscillations that this function G can have at different scales. So this is a very nice situation in the p-adic setting. But it turns out you can do something quite similar for locally random groups. So this is going to be a little bit messier. So you don't really get this sort of nice, clear-cut orthogonal decomposition, but you get something similar. So here we need to pick a sequence of scales, which are defined in this way. So you pick some fixed number eta naught less than 1. And we look at these powers of eta naught, so eta naught to the power a to the I, where a is some fixed large number, depending on the group that we're working with. And we can define the family of projections from L2 of G to L2 of G, which are essentially defined in this way. So you take that delta naught is just convolving with the normalized characteristic function of a small ball. And each one of the subsequent delta I's is obtained in a similar fashion as in the previous one. So again, what we would like to understand is how does this function kind of oscillate at scale eta I. So these functions also satisfy sort of almost version of the previous ones. So they don't, for instance, average to 0 the same way that the one in the previous slide we had. So if you look at delta I of G, and if you flatten it at scale eta J, well, you don't get 0, but you get some contraction. And then we also have this kind of almost invariance property that delta I is invariant under, if you convolve it with eta k for k bigger than I plus 1, then this would be almost invariant. And again, you have this decomposition of this function G in L2. And this sort of motivates the following definition, which is the definition of living at a scale eta. So these are the functions that if you kind of average them on a large ball, so a ball of radius, let's say eta to the power 1 over a, you get almost 0. So so the function, there is enough cancellation in a large ball to make sure the function, the integral would be small. But the functions, they don't have kind of small oscillations, in the sense that if you look at a ball of smaller size, and if you average up over this smaller size, this is going to be very close to G. So these are functions that do have oscillations to give you enough cancellation at this scale, but they don't have oscillations at smaller scale. And somehow the rough idea of the picture is that you can kind of decompose your function into this family of functions, delta I of G, which each one of them sort of captures oscillations at a particular scale. And one of the results that we proved in the previous paper was that you can essentially understand spectral gap by looking only at functions that live at a particular scale. Namely, if we can show that for all the functions f that live at scale eta, if we apply the random walk L steps, then you get a contraction where L is just bounded by the log of 1 over eta. So L is basically what it should be, so of this order. Then you get spectral gap. So then you know that for every function f, which is orthogonal to a finite dimensional subspace, you get the contraction after convolving with mu. So mu star f, this is just p mu of f, is bounded by some constant less than 1 times the L2 of f, times L2 norm of f. And this is true for every function in the sort of finite codimensional space. And in the complement of that, which is a finite dimensional space, we have some spectral gap. So it's a finite dimensional space, so there is no problem. So we get a spectral gap for it. And in this recent work, so I don't have time, unfortunately, to go over the rest, but essentially what we did was that we used the fact that if you, let's say, if you know that, so now you have a measure and you know that the projection of this measure on two components has a spectral gap, what we do is that we take a large convolution power of this measure to make sure that this measure is sort of a measure on the group G, which we don't understand, but we know that its convolutions, if its projections to the G1 component and G2 component, they are very close to the Haar measure. So, and then in the next step, what we do is that, so we use some argument, which is based on some combinatorial construction, to show that you can, in fact, replace this measure by another measure, which is whose projections are exactly the Haar measure. So we have a measure whose projections are close to the Haar measures, and instead of working with this measure mu L, we replace it with another measure whose projections are exactly the Haar measure. And then we basically try to show that if this measure does not give you a spectral gap for functions that live at a spectral at a specific level, then out of this you can construct a local homomorphism from G1 to G2. So this is some additional work which I really don't have time to get to, and maybe I just stop now. Thank you very much for your attention, and sorry for going over time.
Okay, thank you, Keivan. I think we're good. Any quick questions from the audience at all? Okay, well, things since we are indeed close to being out of time, let's thank Keivan again. This was a very informative talk. I think I'll look at the paper to see some details. So here goes the round of applause, virtual or not.
Okay, thank you.
And yeah, and there are a few talks left this semester. Hope you guys will join.